The network media that we're most likely to work with as we're maintaining a local area network is twisted pair cabling. And let's think about what it means to have twisted pair cabling. As you notice on screen, we have a pair of wires that are twisted together. And the twists are there to protect the wiring from electromagnetic interference, or EMI. And you'll notice that the different pairs of wires have a different number of twists per inch. Again, this is done for electrical characteristics. We're trying to prevent electromagnetic waves from being picked up by this wiring. And also, we don't want these wires to become antennas and start radiating. If we start transmitting data at a high rate through twisted pair cabling, if the twists are not tight enough, we become an antenna and we could start interfering with other devices. We don't want that. And when you hear about twisted pair, often you hear the term UTP for unshielded twisted pair, but there is another type, and that's shielded twisted pair. Let's contrast those two. Very popular back in the token ring days, shielded twisted pair had a metallic shielding around the twisted pair cabling, giving it increased immunity from electromagnetic interference. But it was more expensive. After all, we're wrapping the wires in a metallic coating that cost money. And with cost being one of the reasons, unshielded twisted pair really grew in popularity, and that is by far what we see the most of today. Even with unshielded twisted pair, we can still make ourselves somewhat immune from electromagnetic interference, EMI, just by, as we said earlier, creating a sufficient number of twists in the wiring. And this is by far the most common type of local area network media that we're going to find today. And on screen you see that we have different colors of wires inside of this unshielded twisted pair cable. There is actually a standard that says which color of wire needs to be connected to a specific pin on an RJ45 connector. The original standard was developed back in 1991. It was the TIA, the TIA/EIA 568 standard. By the way, TIA/EIA, which people commonly pronounce as TIA, that stands for Telecommunications Industry Association/Electronic Industries Alliance. That standard, which has now become known as TIA 568A, was updated in 2001, and that update is referred to as TIA 568B. And if you want to do an internet search to get the specifics on that, that can be a guide for you if you need to put an RJ45 connector on an unshielded twisted pair cable. The picture that we see on screen is from a particular category of unshielded twisted pair. This is a category 6A cable that we're looking at. Let's compare some of the different categories. First, we have category 3. Category 3 was often used in telephone, in PBX, and private branch exchange installations. And when Ethernet started to catch on with unshielded twisted pair, what you would be able to do is just use your existing telephone wiring to connect up to the network. You could be using 10 base T devices, which would give us 10 megabits per second. However, category 3 isn't sufficiently twisted for the kind of throughput that we would need for fast Ethernet or 100 base TX. Category 3 could go a little bit above 10 base T, however. If it was used in a token ring network, it could give you a speed of 16 megabits per second. But still, that's not enough for fast Ethernet, 100 megabits per second. That's where Category 5 came on the scene to help us out. With Category 5, we can run at 100 megabits per second for 100 base TX networks. And by the way, even though this isn't done very much, Category 5 cabling could even run at a speed of 155 megabits per second for ATM installations. ATM standing for asynchronous transfer mode. We don't see that much in local area networks, however. So generally, Category 5, that's going to be great for 100 base TX. However, nowadays, it's common to get a network interface card that runs at a speed of 1 gigabit per second, 1,000 bits per second. And Category 5E can give you speeds of 1 gigabit per second. And Category 6 can as well. Category 6 is a little bit better than Category 5E. For example, it may be made of 22 gauge or 23 gauge wire as opposed to Category 5E which might be using 24 gauge wire, but be aware that some Cat6 cable does use the same 24 gauge wire that's used by Cat5e. But Category 6 cabling, as opposed to Category 5e cabling, Category 6 cabling has a thicker insulation. You might have a reduced amount of crosstalk if you go with Category 6 as opposed to Category 5e. And finally, down at the bottom of our table is Category 6a. That's what's pictured on screen. The A stands for augmented, and it can support twice as many frequencies as Category 6. And as a result, it's starting to be used in 10G base T, 10 gigabit per second networks. That's a speed of 10 billion bits per second. And we mentioned that this unshielded twisted pair cable is going to have an RJ45 connector on the end of it. Well, here's a picture of an RJ45 connector, and if you count, there are 8 pins. We had 8 wires, and there are 8 pins on this RJ45 connector. However, Ethernet, by default, is only going to use 4 of those pins. We're going to be using pins 1, 2, 3, and 6. There is a pair of pins, a pair of wires that we use to transmit data, and a pair of wires that we use to receive data. And if we get a regular Ethernet cable, like a Cat6 or Cat6a or Cat5 or Cat5e cable, and we try to interconnect a couple of traditional switches, we might run into an issue. Consider this topology. We've got a couple of Ethernet switches interconnected with a regular straight-through cable. And by straight-through cable, I simply mean this. I mean that pin 1 on the RJ45 connector on one end of the cable, it connects to pin 1 on the other RJ45 connector at the other end of the cable. And pin 2 goes to pin 2 and so on. The pins match up. Here's the challenge with that. Both switches, in this case, want to use the same pins, the same wires to transmit. And they want to use the same pins to receive. That's not going to work, is it? Because if I transmit from one switch over my transmit pair, it needs to show up on the other switch on the receive pair. Therefore, we could have issues with a straight-through cable. Instead, we might need to have a crossover cable. A crossover cable takes pins 1 and 2 and connects them to pins 3 and 6 at the far end. And pins 3 and 6, they connect to pins 1 and 2 at the far end. That way, the receive pair on one side of the cable, it gets connected to the transmit pair on the other side of the cable. Transmit goes to receive goes to transmit. We're able to interconnect our switches. This type of connector that we might see on a switch or we might see on a PC, it's called a media dependent interface, or an MDI. However, a feature showing up in a lot of Ethernet switches these days and widely supported on Cisco's newer Ethernet switches, their Catalyst switches, it's a feature called MDIX, Media Dependent Interface Crossover. If a switch port is configured for MDIX, it's going to be able to determine which pins need to be used to receive data and which pins need to be used to transmit data. That means that if one of the switches in the topology on screen had its port configured for MDIX, or if both switches did, we could use a straight-through cable. Even though it looks like we would be connecting the transmit pair on one switch to the transmit pair on another switch, we actually would not, because MDIX would notice that, and it would convert that transmit pair into a receive pair, and the receive pair would be converted into a transmit pair. It can dynamically shift the roles of those pins depending on what it detects it's receiving from the far end of the cable. Again, that feature is called MDIX.